Thank you so much, Jose, for taking the time and joining me on the show today. I found your blog, Nintil, and specifically your post on longevity called the Longevity FAQ, and it was one of, if not, the best kind of state of the arts on aging that I've seen. I just had Jack Harley on a couple weeks ago, actually, and that's those are the two that come to mind, at least as of late, that I think are just awesome references for people who are looking to get into the space. So I'm super excited to talk with you today. Besides the longevity post, you've also just written a ton, which I have, a lot of respect for, having written some myself. And you just seem like a super diligent researcher and writer. So first and foremost, would love to kind of hear your story from as early as you're kind of willing to start to where you are today, writing for the most part, and then hopefully we can spend some time digging into aging and things like that as well.
Okay, yeah, it's great to be here. So at first, kind of and most people know me online as a writer of Nintil, the blog. My actual kind of career, like professionally, started well, back in the day, doing various things involving electric vehicles and like software engineering, machine learning, data science. And through all that time, including a brief stint in a startup and then at Twitter, through all that time, I had been just very interested in various topics. From time to time, I come across things that to me, they either don't seem very clear or I see as in part of the public discourse some things people believe that I don't think if they are, I wonder if they're true or not. I come across within from experts some things that strike me as like experts like disagreeing with each other, and I wonder what's the truth here. So I've been like writing about those, so trying to figure out what's true and correct in across various fields, and that's more or less the driving force for Nintil. And now, since last year, I've been able to be able to work full time on Nintil on various projects around kind of improving science and figuring out how to get to accelerate longevity research and stuff like that.
Yeah, so you have a really interesting sort of intro to the blog where you write about, I'm not sure if this was in the intro or elsewhere actually, but you write about like how you want to have the best blog on the internet by your own standards, which I think is a really good way to put it. Like I think a lot of people conform to sort of a generalized version of success, but you have like a very defined version of what's successful in terms of the blog for yourself, and that's sort of what you're trying to meet. And I think by the standards that you've set, you're doing an awesome job. I mean, you basically, to your point, kind of collect absolutely everything there is to sort of consume and learn on a given topic, and then do an amazing job of reconciling conflicting points. Can you talk a little bit about like your strategy, just from like a very general perspective, not even necessarily related to the longevity FAQ, of taking points from like quote unquote experts in a certain field that are totally opposite and saying different things are facts, and sort of getting to the bottom of things, or maybe not even, reconciling it, but at least framing the 2 points separately?
Yeah. Um, so when I'm writing, I like, or sometimes the reason I write something is because I come across some claim. This might be in a podcast, it might be in a book I read, it might be in some paper, and then I wonder, okay, is this true? So then my usual starting point is, well, it depends on whether or not it's a new area for me. So some may be surprised to learn that longevity, I've only kind of really been into kind of longevity for like the last 2 years, maybe. It's like I have not been like 10 years, like full time on this. It's very kind of very recent. Um, but if it were like a new field, then I would have to, it will be different. So for an existing field, I will typically just go into Google Scholar, and then let's say that I will try to find either evidence for the claim, or if the researcher is citing a paper, I'll just go and read the paper and then assess its quality. I will also try to follow, um, for one given piece of evidence, try to follow and find everything that ever cited that paper, Because, for example, someone may give some evidence that X is true that was published 10 years ago, but maybe 5 years ago, someone else actually disproved that other thing, and whoever was whoever was citing the old research forgot to actually investigate that actually things have changed since then. So I try to do that. I also try to kind of follow the whole stream of citations all the way to the present. So if someone was published in, let's say, in the 60s, I try to even just follow all the threads that emanated from the paper all the way to the present, trying to follow. This is kind of difficult to find which are the good papers to read, because, of course, I cannot read all of them. I also try to find different kinds of evidence, not only academic literature. So sometimes you find very illuminating comments on places like Reddit or even Twitter. So sometimes you find that researchers themselves, they will make very clear statements on Twitter. For one of my recent articles, for example, which I cited this researcher called Pierre Azoulay, about whether or not it's better to fund researchers like for fund people instead of funding projects kind of approach. And if you wonder if the approach that is discussed in the paper can scale, the answer is not clear. But on Twitter, he has said, "Oh, this probably cannot scale." So you can get a more direct view onto people's beliefs through things like blogs and Twitter and Reddit instead of like formal academic papers, and that also can be very very valuable. These other sources can also be very helpful to kind of indicate new leads and new directions for me to do research around a topic, because sometimes to fully comprehend and frame a given claim, you have to understand its kind of surroundings intellectually, to kind of like put together all the different threads there. And then lastly, I guess, once I publish the articles, I to try to keep myself honest. So you're mentioning earlier that Nintil tries to be the world's best blog. So part of this is saying, okay, well, I'm writing a lot. I'm putting a lot of claims out there. So, but on top of that, I do not only want to seem correct and right, because after all, I assume that most people who read Nintil do not read all of my citations. So maybe I could be bullshitting everyone and no one would figure out. So to try to avoid this, I try to create an incentive for people to fact check me. And so for every mistake that is on Nintil, I pay some amount of money. So if someone finds a mistake and wants to claim the money, and I also keep a running log of all the mistakes that I've made and how much money I have paid. And that way, also, if maybe even trying to thoroughly assess some evidence today, maybe if the conclusion is points in one direction, but maybe if next year we got some new evidence pointing in a different direction, maybe having this mechanism of accountability will probably help me to actually change and keep things up to date. Because if not, people are going to be coming for my money.
Yeah, I saw that you were doing that. The what was it, like the "Prove Me Wrong, Earn Money" was the slogan,
Yeah,
I think.
yeah,
And
that's the one.
it's amazing because like I mean I personally haven't seen that anywhere else. And on the one hand, it's like almost the blogger version of the company policy, which is like return within 30 days. It's like basically daring people to call you wrong, and if they can actually do it, that and make an improvement or a recommendation for improvement to make it more true, then you actually pay them. So it's like just really puts a stamp of approval, I think, on how much diligence you do and how much care you put into getting things right, and getting all the facts in there, and citing the evidence appropriately and whatnot. Um, I think it would be great to talk a little bit about how you got into aging and longevity in the first place. You mentioned it's not something that you've been paying attention to for a decade, but I understand that like the first initial spark that didn't drive you to go deep, but sort of introduced the topic to you was reading Aubrey de Grey's book Ending Aging, like maybe a
Yeah,
decade ago.
yeah. So maybe 10 years ago, I did read Aubrey's book, and it's like, oh, this is kind of interesting and very cool. But for some reason, I didn't quite like follow up on that. I kind of like left it there. Like, in the same sense that you can read books about weird math or like cosmology and whatever. It's like, okay, fine, that's kind of cool, but it didn't really fully get me into that. I think the book that actually did it, well, there were like two events that uh, or rather, maybe the reason that Aubrey's book didn't do it is paradoxically because on Aubrey's view, everything seemed more or less clear. So the Sense Foundation, as I guess listeners would know, is they have a plan for aging. They have a category of damages that they think that if we fix those damages, then we can effectively fix aging. And the book describes what those damages are and how they're going to fix them. And it seems like, oh, this seems like it's a solved problem. Oh, it's kind of everything is sorted out. Cool, it's good to go. But things are one, it's kind of complicated, and then second, there are so many fascinating things in biology intrinsically. So no, I think, and ultimately what got me into bio were a combination of things. One was the talking with Laura Deming a bunch of times, and I asked her, I was asking, so we have all of these interesting interventions to reduce aging, right? So you have some people have like resveratrol and sirtuins and NAD and like reprogramming and like parabiosis and many things people have proposed to reverse aging. But what if you do them at the same time? What do we know about the effects of combined interventions? Not much, it seemed, from what she told me, other than some experiments, some very niche experiments doing gene editing in C. elegans, these tiny worms. We don't know much about combined interventions. I was like, I wonder what you could achieve if you combine these interventions. So that was one. And then I guess in parallel, it was learning about this idea of partial epigenetic reprogramming, which is one of the coolest hot areas right now in the longevity space. I was like, wow, this thing is actually possible. Right? How does this work, and what are its limits? So that kind of got me going initially to try to see how all of these things fitted together. And maybe perhaps there was also one other thread as well that got me into longevity and biology in general as well, which is that a few years ago I published, maybe 2 years ago, I published this brief blog post where I said that maybe physics is kind of dead, or rather that fundamental physics is in some sense dead, in that we are not going to see anytime soon another quantum or relativity revolutions that are going to be then put to use. So from relativity, for example, we could use it for GPS, and quantum mechanics we can use it, for example, for semiconductor design, or for building like whatever has to do with very tiny, let's say, wavelengths or whatever. But but at the same time, in that post, I said, well, biology seems to be making a lot of progress. We live in a golden age of biology. Like we're discovering new things every day, practically, things that are maybe even paradigm changing. And then at some point, I make the connection. It's like, well, if I do believe honestly that biology is the future, I should understand how it works, how it feels, the structure, how funding works here, what are the hot areas, and so forth. So that ended up doing it for me, and then I ended up like in this rabbit hole that's like the more you get into it, the more it keeps going.
Yeah, so you're obviously like super smart, and it's funny just to hear you talk about these things. You basically got into biology because you figured out that you thought, physics is maybe dead, quote unquote. And then, most people might be like, oh, okay, like that's cool, and kind of move on with whatever their day job is. You decided to basically teach yourself molecular biology, starting with a big textbook, which I know because I bought it at some point myself with the ambition to potentially read it, and never did that. And then you went and you kind of filled the gaps with Khan Academy. Can you talk a
Yeah,
little bit
that's
about
right.
that learning process? And I'm just curious, not a lot of people take it upon themselves to learn, like an introduction to something, let alone sort of become an expert in a subject. And you were able to kind of do that with, maybe your expense was like $120 or something on the textbook, and then the free Khan Academy video. So it's a sign of promise for what can be done in the future in terms of like self-education, I think. And it would be great to hear about your experience. And then separately, or not separately, but relatedly, if you had to kind of do it again, if there's anything that you might change.
Yeah. So first, I wanted to add one thing from what I said before, which is that because some people, when I say in a very clickbaity way that physics is dead, they kind of misinterpret what I say. So I do think there are some areas like topological matter that are probably very interesting, and will actually get interesting applications in the future. And I guess like if people are interested in reading more about what do I mean by physics is dead, I guess they should go to my blog and then find read those blog posts, see exactly in which precise meaning I'm intending that statement. Because I don't mean that we should like stop doing any physics and it's kind of completed, and by no means. Okay, so on the educational side, so how I did it, yes, as you mentioned. I got the textbook largely because a lot of them said, "Oh, this is the textbook that you have to read to get into bio," and the best approach to bio is starting from the molecular side of things. I think molecular biology, I think from the bottom up, and I basically, so when I approach a new field, I have this idea that you are initially not trying to necessarily learn facts, but you're trying to build a map of the territory. And when you go into the field, you don't know what the territory looks like. You have some vague hints that there are some things you're going to find and understand eventually, but you don't know what is important. So when you're reading a textbook, um, I personally do not take notes. I think because the taking notes, or to me, like taking notes means that you already have some kind of framework to understand what you're reading, and you're taking notes about those extra or interesting things that are there. But to me, without it's like a chicken and egg problem. Without actually being or knowing the field, it's difficult to know what's going to be relevant or not. And biology is full of, there are so many genes and proteins and processes, and it's like, are you going to try to learn everything? Are you trying to try to go deep on every single word you understand, going into that? So instead, I said like, okay, I just literally just read the book, no notes, just reading the whole thing. I probably actually skimmed or skipped some sessions, sections. I won't say that I actually read literally everything. Um, but then that book gets you an idea of more or less how everything works and how complex things are, more or less, to form something like a low resolution picture of the given field. And then I said, okay, well, now let's pick one area and go deep in this one area, and let's get a more high resolution view around here. And then let's pick a different area and let's get another picture here. But you can only do that because you have this map that more or less tells you what's the interesting next area to visit. I guess to some extent, this is the going to my machine learning side. This the same thing that you would do if you were doing Bayesian hyperparameter optimization, where you start with you sample one combination of parameters, and then that gets you an idea of how optimal it might be, and then you can try another area that the process tells you that it's optimal to sample next, and so on and so forth. So on the learning side as well. So yes, so the key learning came from initially that textbook and Khan Academy. Largely, I was going through the textbook, and then when I thought like, oh, I find myself not really grasping what the textbook is telling me, I wouldn't go to Khan Academy to get a more solid foundation there. And then at some point, I was able to then switch to reading review papers. So I think review papers are great in that they in themselves are maps of the territory, or a specific territory rather. But one usually has to read various literature reviews because typically different labs have different interests and they will skew the reviews one way or the other. So you want to read many to avoid overfitting to one particular point of view of one given field. Also to try to get like a more, just to cover more areas within the field. So from the reviews, then I said, okay, well, now I'm kind of ready to see exactly all of these reviews, the kind of papers these reviews are built on. So then I just moved to specific papers that seemed interesting. So for example, recently there was this paper from David Sinclair where they were able to partially restore vision to a mouse using this thing called partial programming. It's like, oh, this partial programming thing seems cool. Let's find the key papers in this area. And I found one or two and I read them. And I got myself acquainted with not just the claims the papers make, but also what kind of experiments and or typically called assays. How is it that they justify these claims are, and how robust are these techniques? So this is so I think that definitely one can get quite far just from publicly available information and textbooks and videos and I think we're also in a golden age of that where so you had Aubrey de Grey, for example, in this podcast, and so people are very open to talk about their research and their field. There are, however, I think some things that you can only get perhaps either through podcasts or by going to like private seminars or by emailing researchers, some things that are kind of implicit in the fields that are not necessarily obvious from the outside. I guess one example in the aging field is this idea of the hallmarks of aging. So if one naively looks at the aging field, one finds these so-called hallmarks of aging that many papers cite. So they will cite things like telomere shortening or epigenetic dysregulation or loss of protostasis or various things. And then you may think that, oh, like this is aging. This is aging is 7 or 8 things. but not quite. And actually, if you asked anyone in the field, they would tell you that the hallmarks is just like a grab bag of like things that back a few, maybe 7 years ago, some researchers thought that more or less those things had to do with aging, but they were not intending to be neither comprehensive, not trying to find the true root causes of aging. They were just trying to identify some things that were useful and interesting and had some evidence behind to say that they were hallmarks, but they didn't intend to say more than that. Now, this is not, as I said, this isn't obvious just from reading. So to learn this, you have to actually kind of, you can learn maybe 80% or 90% of everything just with public information. The extra 10-20%, you actually have to go to talk to researchers themselves to kind of get all those nuances that have not made it to the public yet.
Yeah, it's interesting. I'm sure there's some questions that sort of come up for you in kind of evaluating all the publicly accessible knowledge, whether it's, the textbook or Khan Academy or podcasts and blogs and the like, questions that come up that simply aren't answered in the public sphere that maybe you bring to researchers and can get that final 10%. But it's really interesting I really like the concept and the framework of like not taking notes when you first enter a field to build that map of the terrain, as you said. That's just like a really interesting way to approach it. I think a lot of people don't approach it that way, and so obviously you've been very successful in being able to pick up expertise in a field from zero to where you are now with aging. So I think certainly something to be said. Everyone might have their own learning style, but certainly seems to be working for you. I think now, it'd make good sense. And I'd be interested in sort of just diving into aging, and your longevity FAQ is quite long and quite detailed. And so I'm somewhat stumped on like where to start, but I think the best place might just be to talk about how you think about aging sort of definitionally, and this field from like a very high level, like what is the point in slowing or reversing aging? And it seems obvious, but I'm curious to hear sort of how you introduce that.
Yeah, so maybe on a meta point before introducing aging, there is surprisingly a lot of, if you go and ask researchers, there is a lot of discussion about what is aging question, even to the point where last year there was an article published that is quite interesting that argued that, and this was from some gerontologists in the field itself, that maybe there is no such thing as aging, which is kind of an interesting take, and it's an interesting paper that I recommend reading. I don't know if we can link to it or something. But basically, the way I think about aging is we're first thinking about the question of what is life, rather. And if you think about life at a very abstract level, you find a set of processes in any organism that try to upkeep some states, rather, let's say. So if you take, for example, a healthy human being that is in an adult stage, you can say that, for example, okay, there are some healthy ranges of things like LDL cholesterol, of like levels of blood glucose, levels of muscle strength, levels of memory, cognition, reaction speed to stimuli, bone strength and bone density, and so on and so forth. So there are like many parameters we could measure. So you could define health as one point in this multidimensional space, and this kind of point, of course, is changing. So if you take we have circadian rhythms, we have rhythms that are longer than circadian. I think, for example, growth hormone like spikes during the day. So, of course, these parameters of healthiness change over time, but you could define more or less something like a region in this space of parameters that more or less define like a healthy state. So, aging would be a drift from this space, and it will be a drift that you cannot attribute to typically one single cause. So, the way that an organism stays healthy, we have. Is that so you have all of these interconnected systems. So we have the immune system, and we have the brain, blood circulation, muscles. So everything, you could decompose all of the systems in a human body, let's say in our own case, into different subsystems that are more or less loosely connected to each other. So there is no like isolated like cell that's there, meaning their business. Everything is to some extent tied to everything else, and each cell has a function. So they do work. They get some energy. They perform some tasks. So these tasks may just involve maintaining themselves, producing new proteins, degrading misfolded proteins, trying to digest it's like various waste products, and then excreting outside waste products as well, trying to repair DNA. So cells are trying to like stay again within their own healthy parameters. The way they do this, they have all sorts of mechanisms to try to do so. But there are two problems with this. One is noise. That is that biology is stochastic. So these two problems, just to clarify, these two problems are to me are what the root causes of aging are. There are two broad reasons for aging. So case one is noise or entropy, as we may call it. Processes in biology are stochastic to some extent. So a cell, if you could zoom into a cell, you have you will see proteins just bumping into a cell randomly. And even though a textbook may say that this protein reacts with this other protein or an enzyme to do this thing, that's what they actually mean is that that reaction is particularly favored, that it happens more often than not, or very often, and that a given protein may not or may very difficultly interact with something else. But in practice, it could. In practice, any protein could react with anything else. So we have that. So then the odds that that you're going to get something that it was not intended by the cell. So it's like, for example, DNA mutations, right? So cells don't purposefully induce DNA mutations in themselves. Like sure, cells in the immune system might do some recombination to try to produce lots of kind of T cells that can detect many kinds of pathogens. But typically, cells don't try to kind of change their DNA. But DNA mutations happens. They happen because of radiation, of noise. Maybe some protein just bumps in the wrong way against the DNA, and you get a mutation there. And the cell has no way of knowing that what used to be a T or a C is now an A or a G or whatever. So you get these DNA mutations. DNA mutations, as it happens, and as Aubrey de Grey also noted in his book, they don't really matter much for aging, except in as much as they lead to cancer. But you can also get other kinds of damage at the level of the epigenome and also at the level of misfolded proteins. Now, misfolded proteins are just proteins. Like proteins are supposed to fold in a given conformation to perform their function. When they don't, sometimes they may actually lead to disease, as is the case, for example, with Alzheimer's. But and then here we could hope, well, to some extent, cells can actually repair. They can try to fold again, or they can digest and eliminate these proteins or these aggregates that form in cells. But again, these processes are not perfect. To give you an example, if we take atherosclerosis, which is the accumulation of plaque in our arteries, which then leads to things like a stroke or various kinds of cardiovascular disease, atherosclerosis, this accumulation of cholesterol, starts to build up from the time when we are born. So this is not that our repair mechanisms break down. It's that by design, we cannot get rid of all the cholesterol that gets in our arteries. So this means that even if we could just kind of stay in a kind of like as if we were like an 80-year-old for life, even then will there still all this kind of noise of various sorts will still accumulate, ending up leading to the disease. And again, this is just a consequence of to some extent evolution. Like the evolution didn't give us like repair and maintenance mechanisms to address literally everything that happens in ourselves. And that's, for example, one of the things that the Sense Foundation has been looking into. Is like, well, if our cells cannot degrade and excrete particular aggregates inside of them, maybe we can engineer new enzymes to do so. The fact that evolution was not able to do so doesn't mean that we can like rationally do some clever, intelligent design, then put it in a gene therapy format, and then try to fix that. This is, of course, an extremely difficult problem, and not intending to mean here that this is kind of trivial, but this is one thing that one could do. The second broad cause for aging that I see is what some people have called quasi-programmed aging patterns, or quasi-programmed aging for short, or in some other context, antagonistic pleiotropy. So this is the idea that there are some things that end up leading up to disease that are not random, that our body in a way intends, or it's harming itself in some sense. And a version of this is the involution of the thymus. So the thymus is this gland that's that's located in our chest, in between our lungs. And the thymus, its role is to take thymocytes, which are like T cell precursors. These are like T cells are like key cells in the immune system. So these precursors are made from stem cells that reside in the bone marrow in our bones. So that they're made in our bones, then they go into your blood, then they loop around, they go to the thymus. In the thymus, they are trained, so to speak. The thymus has some quality control on these T cells to make sure that they're not going to attack our own body, and that to make sure they are effective against pathogens, and then they can go out as T cells and into the circulation. And actually, that's where the T comes from thymus. The problem is that this the problem or advantage is that the thymus shrinks and becomes replaced by fat as we age. So maybe by the age around puberty or a bit early, the thymus has mostly disappeared. So we are not producing more T cells. We are left with whatever T cells we were left when we were that young, and that's everything we have kind of for life. The reason for this is that the thymus is very expensive from an energetic point of view. Doing all this quality control, so maybe out of 100 thymocytes going to the thymus will maybe 90% will get rid of them and kill them because they are not good enough to be good T cells. So it's constantly taking lots of cells and then getting rid of them and making more. And so from an evolutionary point of view, evolution said, well, if you're a hunter-gatherer and your life expectancy, you don't live that long anyway, and you more or less stay in the same area, and you don't have time to develop cancer or to be exposed to a whole new kinds of new pathogens every day, then what's the point of having this very expensive organ? It will be more efficient if we can just make it disappear as you age, and then we can use that energy for something else, like reproduction. So that will be one example of quasi-programmed aging. There are also other funky examples in C. elegans that are more striking. Like C. elegans will, for example, the worm itself will eat its own, or rather, not with its mouth, but this worm will kind of eat its own intestine to make fat as part of the same process that it uses to create the eggs that it will then lay to reproduce. But even when there are all the eggs have been laid, it will still kind of consume itself to try to keep doing this, even if there is no reason for the worm to do anything like that. Just like the case that the same kind of program that leads to health, if you continue that program beyond adulthood, that also leads you to aging effectively. So this is mostly associated with this protein called mTOR, which is a master regulator of metabolism and proteostasis. And mTOR is like, it sounds like it's great, like mTOR kind of drives like making more proteins and more cellular divisions and stuff like that. But putting that brake on mTOR, saying to the cells like, no, like you have to chill in some sense, that actually is probably the most validated and well understood intervention for longevity, at least in mice, and it's what's behind things like caloric restriction or rapamycin. So those are the two causes of aging. Now, this does not mean that those are the two targets, that we should target those things for clinical purposes. There might be other points that are easier to target. So, for example, you will never be able to get rid of noise in biology. It's kind of intrinsic to the way that biological systems work, and even potentially would say that's the way physics ultimately is. So you cannot fully reduce that. So you cannot click a button and then we're going to design a way to make every protein fall perfectly, and like there are going to be zero aggregates and like zero cholesterol in the arteries, like it's going to be super perfect. That's not realistic to get rid of all of that. But we can say, okay, well, we can detect maybe kinds of damage locally, and maybe if we remove those, maybe that is more targetable than just trying to go to the root cause. Likewise for the thymus, maybe it's difficult to kind of reverse or the involution, but maybe you could, for example, try to just find a way of transplanting or generating, let's say, in vitro new thymuses and then transplanting them back. Or sure, you could also eventually just try to, with a gene or cell therapies, to try to bring back our actual thymuses, which is what this study from 2 years ago from this guy called Greg Fye tried to do, using growth hormone and other things to try to regrow the thymus and try to see if that could lead to rejuvenation as measured by these so-called methylation clocks. So yes, so aging. And maybe just to wrap up this, if I said earlier that there are various kinds of disease, so you can think of Alzheimer's, of cardiovascular disease, cancer. And if you can think of the human body as built up of various loosely coupled systems, the diseases are similar. And this is maybe the key insight of so-called neuroscience, or the science of aging and longevity. The idea is that by addressing a common set of causes, we can address many diseases at once. Now, this doesn't mean that every disease is caused by exactly the same things in the same proportion. So I guess, for example, if you take atherosclerosis and cholesterol, it's like, well, the buildup of cholesterol has nothing to do with, let's say, or doesn't seem to have much to do with cancer, but it does in the context of cardiovascular disease, because you have cholesterol in your blood, and your blood is in a particular system within your body. So some diseases are more, so to speak, more tied to aging, to this kind of central collection of processes that are more tightly connected, and others are less connected to aging. So to some extent, it makes sense to split diseases into different categories, and it makes sense to talk about things separately, like and treat Alzheimer's on its own. But the neuroscience point of view, I stress that yes, we can treat this in separately, but we have to acknowledge that all of this stuff ultimately is interrelated. That fixing one thing may help to fix another thing, and potentially even fixing various things at once, start targeting this core set of pathways, can actually impact multiple diseases, and through that increase lifespan and health span by a lot. And just to finish up, just really try this last point. If we could cure cancer, like to cure all cancer, like right now, life expectancy would only increase by like 2 or 3 years, which is not a lot. And the reason for that is that you will still die of heart disease or Alzheimer's or respiratory diseases or various other things. And the point of aging is that we can actually tackle everything at once, and we should do everything at once if we do want to see large effects on health.
Yeah, that's an awesome intro. And that last point that you make is the thing that really sort of makes it click, I think, for a lot of people, which is that if we were to solve cancer or solve heart disease, it's actually only adding a few years incrementally to like the average human health span. Whereas if we can make a 10-15% difference on aging, in terms of like slowing it or reversing it periodically, whatever it might be, it's a much more substantial difference on the human lifespan and more importantly, the human health span. You talked about the two sort of roots of aging from your perspective being sort of entropy and quasi-program aging, I think, if that's right.
Yeah.
And so how do those fit in to, or you know, where's the context like tying together those with, you know, the hallmarks of aging or like Sen's approach to repairing damage? Like you mentioned, it's not practical and seems impossible even to actually prevent the damage, like kind of the random damage and entropy from actually occurring over, you know, humans' lifespans. But Aubrey de Grey's approach and Sen's is basically to go and just periodically repair the damage that's accumulated, and therefore you're sort of you know, reversing aging from a biological perspective over time, and can sort of do that ad infinitum. So curious to hear sort of the context between like the hallmarks, Aubrey de Grey's approach at Sen's, and then what you view as like the two, you know, the two drivers of aging.
Yeah. So as you mentioned, so the Sense Foundation, the starting point of Aubrey's thinking is that biology and aging, they're very complicated, and trying to understand exactly how everything exactly works may take a long time. But at the same time, they think that in theory, it doesn't have to be the case that we have to understand everything about aging in order to treat aging. Maybe it could be, and in his book, he shows that it might be that we already know some interesting targets of intervention that we can use to actually just solve aging. In a similar way, maybe to make a similar point, if you could go back to the Industrial Revolution, we didn't first figure out thermodynamics and then we invented the steam engine. Actually, we invented the steam engine first, and then we tried to understand how it works, kind of from a more detailed first principles way. So with and so Sense comes first taking that what Ori calls the engineering approach to aging. So a way to think about Sense, although I think that this is not framed exactly this way on Sense's either the Aubrey's book or the Sense website. But if you look at why do people die, kind of like from a forensic approach, well, you can point to like cancer, you can point to, again, cardiovascular disease of various kinds, you can point to infectious disease, You can point to respiratory, well, it's thought to be infectious disease as well, and also various like rare diseases that are genetic in nature and maybe they are not quite aging as such. But then, okay, besides that, there are also other things that go with aging that do not necessarily lead to a kind of mortality, like wrinkles in the skin, or the hair getting white. And so then you could go from all of these things. Okay, why does it happen? Why? What is the molecular cause of the hair going white, and what is the molecular cause of this and that? So then, from those causes, then you can take one step back and then try to tie this down to as much as you can. And then Aubrey in his book ended up finding I think there were like 7 kinds of what he calls damages that he found, that he thinks that, well, like these ones, they seem to be easy or reasonably well posed for therapeutical intervention. This again, like the Sense Foundation, and I think that they would agree, do not say that these are the root causes of aging. They just say that these are the best, these are damages that accumulate and that are good intervention points. I guess an example of this, one of the both a hallmark of aging as well as a sense damage category, are senescent cells. So senescent cells are these cells that form when, or a cell will turn senescent for either when it detects that it's getting closer to getting in a cancer state, and it can maybe decide to kind of stop itself from going that far, maybe due to damage due to radiation, and also the other kinds of damage. For example, a chemotherapy can also induce senescence in some cases, as well as telomere shortening. So when telomere shorten, cells may end up being senescent. Now, and then in turn, the senescent cells generate inflammation, which some people speculate that this might be so that kind of it's like a signal for the cell to tell the immune system, hey, I'm senescent and kind of broken. Please come here to garbage collect me. But if you have too many senescent cells and your immune system is weak, then this just accumulates, creating chronic, as they call chronic age-related inflammation, which then leads to various diseases. Now, as I said, so senescent cells are not a root cause. Senescent cells are caused by telomere shortening, for example. And telomere shortening is, in a way, it's so telomere shortened by design. This will be, in a way, part of the programmed kind of set of things. So telomere shortening happens because of the way DNA replicates. By the way it's meant to work, they have to shorten, as well as that plausibly telomeres may serve a protective mechanism against cancer. So yeah, so the sense damage categories, they form a coherent set of categories, as in they are meant to. The claim Sense makes is that if we fix these kinds of damage, we're done, aging fixed, and we can achieve what Sense called negligible senescence. That's not immortality, but it just means that instead of our mortality risk going up with age exponentially, we just stay constant through life. I guess as a thought experiment, the mortality risk when you are, let's say, 8 years old, it's very little. I don't know if I have here the exact number, but I remember that if we had that same mortality risk from when we are 8, and we could maintain that for all of our lives, then our life expectancy might be in the 1,000 years range. Now, if this is workable or not, that's a trickier question, but that's more or less the idea would be that it wouldn't lead to just being forever by design, but it would lead to greatly increased lifespans. Now, the hallmarks of aging, they don't make, well, I would say they don't make any sense, but it's literally, there is no strongly opinionated conceptual framework generating the hallmarks. So literally, the hallmarks of aging is like a hallmark of aging is anything that meets 3 conditions. It has to be something that manifests itself during aging. It has to be something that if you experimentally make it worse, then aging gets worse. And if you make it better, then aging gets better. Now, on these grounds, you could also argue that like LDL cholesterol is a hallmark of aging, because if you get more of it, then your mortality risk goes up and vice versa. But it's not on the hallmarks of aging paper for some reason. So they try to strike a balance between systemic hallmarks of aging and trying to be comprehensive. So they end up with this list of 6 or 7 hallmarks that are to some extent related to or similar to the sense damage categories, but they are not as kind of systematic as the sense ones. So plausibly there might be other hallmarks of aging, or there are many things that you could say they are hallmarks of aging. I guess the point of the hallmarks of aging was different. So the reason these researchers from Spain, actually, the reason that they proposed these hallmarks was to try to like create a kind of map for aging, but not necessarily a comprehensive map, but something more of a tourist leaflet of sorts to kind of say, here are some things that we have found that are interesting to look into. They were not trying to say in the same way that Sense was trying to say, this is like aging is the 7 things. If we fix the 7 things that we can actually fix because we have chosen them so we can fix them, then we are done, and we are good to go. It was not like that. So this is a reason, for example, that I and as well as Laura Deming and that we have talked to and others, we don't quite like the hallmarks as such. I think they served their purpose back then in 2013, but I think it's time to move past the hallmarks framework and have like a hallmarks V2 kind of more maybe inspired by a sense kind of a framework where we actually try to say, okay, let's begin from a forensics point of view, what is life, what is aging, what is death, and then working backwards into various categories. And then maybe if we, which in a way is trying to do again what Sense did back then, and maybe we will find new interventions or new potential targets that we could address to reverse aging.
Yeah, that's interesting to hear because I know when I spoke with Aubrey, I don't want to like put words in his mouth or anything, but I believe he was basically saying that like I more or less came up with like the categories that the Hallmarks is trying to go after well before they did, and then they didn't even really sort of cover all of the categories that the SENS framework sort of goes to tackle in terms of like the types of damage that would need to be addressed and sort of the problems that need to be solved in order to address aging overall, regardless of sort of why these damages are accumulating necessarily. Just what is the problem and how do we fix it, or at least let's try to figure out how do we fix it. So one thing that you brought up was like the possibility if we could sort of have the same probability of death that we have at age 8, we would, our average human health span would be like above 1,000, and I think that's really interesting. And there's this concept, I think maybe like a misconception that people have that aging is like very fixed. But I know, in your writing, you wrote about how animals give us confidence in a couple of ways that's not really the case. One is that a number of animals in the wild live quite long, and actually some of them display negligible senescence already, in that they're not actually at a higher risk of death or certain diseases like cancer, heart disease, Alzheimer's in humans as they get older. They just sort of have a fixed probability of dying throughout the majority of their life. And then secondarily, we've also been able to show in animals that there's treatments and therapies that we can do that maybe they haven't been proven in humans yet, but in worms, which you've mentioned, like the C. elegans, as well as mice, there's already been a number of proven strategies to extending not just like the average health span and lifespan, but the maximum. So could you talk a little bit about like what gives you the most hope from looking at things that have been proven or just occur naturally with animals in that way?
Yeah, so animals are something very exciting to look at, and I think I even at some point I wanted to write a longer article just on aging across various animals, or even aging in plants or aging in microbes, like I said, aging in completely different realms, because definitely nature it kind of like nature has been doing experiments for us for like millions of years, and like even things like CRISPR or techniques, they just we just took them from nature. And so likewise, different species have evolved different adaptations that can combat aging. So for example, in elephants, we can find multiple copies of this gene called P53 that helps them resist cancer. We can also find on naked mole rats, this like some of these animals that seem to display a negligible senescence. We can find this substance that it goes between the cells that's called very high molecular weight hyaluronan, that seemingly protects against cancer, or if a cell gets cancerous, it kind of seems to force the cell or to stop it from replicating somehow. It's not very well understood how it works, but what we do know is that naked mole rats very rarely get cancer, and even when you try to induce cancer through radiation, so to try to just like in a very unnatural way, even then it's very hard to get them cancer. Whereas the same radiation when you do that to mouse cells, then they actually either become cancerous. So there's some experiments now going on to try to, for example, say, well, like this, which again, when we think of biology, is very, very plug and play. It's like, well, what if we take the protein or the synthase, it's called, that is making this very high molecular weight hyaluronan from the naked mole rat and put it in mice? Do we get cancer resistant mice? Well, there are some labs working on that. There is one researcher, Joao Pedro Magallanes. He's also has some work on this cross species aging stuff. That maybe also interesting to check out his work for some more in-depth, even genomic analysis of cross-species aging resistance. Yes, we also have some other extreme examples. I think there are some sharks that may live to like over 500 years, which is like, well, this kind of proof of concept that there are some ways in which you can have a complex, large biological system that like us, they have an adaptive immune system, they have blood, they have circulation. So like all of these things that we have that break down with age, they also have. And so if they can live that long, then it's like, what is it that makes them live that long? Now it's difficult to know directly because it's like having an aquarium full of sharks. It's harder than having a vivarium full of mice, but it's there. They exist, and we have their genomes, so we can study them. Now it is true that it is from our knowledge of animal models. So typically researchers will examine worms, flies, mice, and yeast, and humans. And some primates in some cases, like monkeys. It is easier to make simpler organisms live longer. So, for example, we do have a worm. So we have the 10x worm, the 10 times the wild-type lifespan in worms. This is simply by knocking out a bunch of genes, and we get very long-lived worms with seemingly no impairments of any kind. In mice, they're having some work in generating dwarf mice. These are mice with various kinds of knockouts to either growth hormone or this thing called IGF-1 receptor that causes them to be kind of small, but again, increasing their lifespan by, I don't know if it was like up to 50%, which might be the record for an intervention in mice. Just to get an idea, mice, they usually live no longer than 36 months, and typically a mouse that is 18 months old is kind of already kind of like old. So yeah, I think the good thing though, on the other hand, is that yes, that maybe all of the kind of easy thing that you could do to make us live longer, so nature has already implemented those in us. So I think that we are way more cancer resistant than say mice are. Like mice, typically they all die of cancer, whereas in our case we have other causes of death. But again, as with sharks, mice, they have a circulatory system, an immune system. They don't get Alzheimer's because they don't live long enough. But for a lot of things, you could argue that if you understand aging in mice, and if you could reverse or slow down aging in mice, you have some grounds to believe that you could do it in humans as well. Although the kind of interventions that you would need to do so may be different. I guess an example here, the arteries and veins in mice are very flexible and resistant. So it will take way longer for them to get cardiovascular disease than it would take for us. So you need to, in some cases, use like animal models to try to replicate what goes on in humans. And then there are other challenges that maybe we don't know yet that maybe will only be relevant in the future. So for example, there's this very rare disease that's called transthyretin amyloidosis. This buildup of this protein called transthyretin in blood that is extremely rare. But if you live long enough, this is one of the causes of death that's common in supercentenarians. These are people that live over 110 years or so. And you only see this really if you live a very, very long time. But then it's like, well, let's first fix basically, if you could fix at least cancer and cardiovascular disease, and infectious disease, if you could fix those three big categories, then we can then worry about, okay, what's next? What are the other key categories of disease that will come next after everyone is being healthy at 100 years old, and then we can keep going.
Yeah, so what do you think about when you think about like what's working or what's been proven to work or at least shown signs that it could work versus also what is just sort of promising and you think maybe likely to prove that it could work in the future? There's things that are further along down that line, like caloric restriction or doing intermittent fasting to sort of achieve the same result or a similar result, arguably. And then there's things like senolytics. You mentioned senescent cells earlier, sort of the ability to kill or like delete these zombie cells in the body that lead to, certain signs of aging, if I'm getting that like sort of right. And then, there's a bunch of other things as well. I'm curious to like drugs like rapamycin and metformin. I'm curious to think about like what do you think are some of the most promising therapies and things to do in the near term, and then sort of what could be on the roadmap thereafter.
Yeah, yeah. So I like to kind of split aging interventions in two broad groups. One is what I call aging 1.0. This is the most well studied interventions and pathways in the longevity space that have been known for decades, and this usually revolve around uh, a salad of keywords that involve mTOR, AMPK, IGF-1, and insulin, which in general are grouped as the nutrient sensing pathways. So when people talk about caloric restriction or rapamycin or intermittent fasting in some contexts, or some more drugs that are more obscure like acarbose, which to some extent works through, again, caloric restriction by limiting the absorption of carbohydrates, these are all similar into how they work. And we know more or less how they work, and we also know that they work in most things you give it to. So if you give, for example, rapamycin, so rapamycin is so called because it targets and inhibits this protein called mTOR, which it's actually called mammalian target of rapamycin, which is kind of one of what's meant for the other. So if you target mTOR with rapamycin, you can extend lifespan in yeast, in flies, in mice, in worms. It has not been done in monkeys, and we don't have like a solid study in humans. There's an ongoing phase 1 safety trial for rapamycin in longevity called the Pearl trial, but we don't have like solid experimental evidence that this work. But a lot of people expect that it should work given everything that we know. Actually, one researcher even went as far as claiming that if rapamycin doesn't work in humans, everything we know about aging is wrong, kind of thing. Now, these interventions have their limits. They may slow down aging. They may perhaps reverse some parts of aging, but they are not as comprehensive as we may like them to. I think it's a good starting point in the same sense that you may want to have a healthy diet and exercise and so forth before try new things. So I guess it's a good starting point, this whole aging 1.0 kind of like metabolic approach to aging and longevity. And here I will probably also add that I don't think metformin is going to work that well. Sure, there is some observational evidence that metformin might work, and there is a trial called the TAME trial to try to validate metformin as a longevity drug that is currently recruiting. But I don't have high hopes for metformin, and actually metformin failed to show lifespan gains in mice when it was administered in this testing program known as the ITP, run by the NIH. This is a huge sample size, like high signal-to-noise ratio experiment run in 3 different labs to try to validate interventions. And metformin on its own didn't really lead to lifespan increases. It did, however, in combination with rapamycin. If you put them together, you get some synergistic effects. But on its own, it didn't seem very impressive. The same thing I may say for things like NAD and resveratrol. I don't think these things are, or rather, they may work like in yeast or in worms, but the evidence behind these things working in humans, I think it's kind of slim. Maybe in some particular conditions they may work, but I don't think from a general population point of view or general aging, I'm not sure these things are as promising as caloric restriction or rapamycin might be. So I think that maybe if I had to say what is the most well-validated one, I'll probably say CR or rapamycin. Now, then there is aging 2.0. This is this second new wave of aging interventions, which is way more varied. And it involves a bunch of things like the ones you mentioned, senolytics. And this is going after damage directly kind of thing. So we have senolytics, which we mentioned. We also have the two interventions I think I'm personally most excited about. One is something that it used to be called probiosis because it was discovered when you join together like an old mouse with a young mouse, and they exchange blood. Seemingly, the old mouse seems to, according to some parameters, rejuvenated, which seems and then from here, this line of research has led to something that now people call plasma exchange. So this is that not apparently what worked is not so much giving young blood to old mice, but actually diluting whatever harmful junk was in the old blood. So in practice, this would mean that you could effectively donate blood, or rather have your blood exchange with saline and albumin, which is a protein that carries nutrients, a very simple thing. Just that apparently has huge, very interesting effects in mice, according to various studies from this lab, the Conway lab. And then there's some ongoing work in determining why is it that this works and to what extent this works and it doesn't. As in, is it rejuvenating or to what extent is it rejuvenating the brain? Is it leading to lifespan increases? If so, to what extent? Is it, or what is something that doesn't work for? And if so, if we combine, let's say, this with rapamycin or something else, can then we fix? Can we keep going and get the synergies? The second intervention, which is probably my actually top one by interest, is partial epigenetic reprogramming. This was the most interesting work here was done in 2016 at the Salk Institute. This guy, Alejandro Ocampo, at the Juan Carlos Ispizo Belmonte lab. And they showed that they could rejuvenate almost like in anything in a, this was not in wild type mice, this was in a mouse that was made to age in an accelerated way, that they could again rejuvenate anything by doing the same kind of procedure you would do to make a cell into a stem cell. If you go halfway, then apparently you can kind of erase and remove all of this damage. It's kind of a very surprising thing that we have only learned recently. This, for example, in the original Sense book, there was no mention of partial reprogramming as a potential avenue to tackle kind of everything, all the damages or many of the damages at once. So now again, there's work ongoing into okay, this thing, to what extent does it work? And does it, because of course, ultimately the effects on lifespans were huge for these mice, but to what extent or what is it that this intervention does not fix? And if so, what is the right combination to kind of keep going and to increase more lifespan? Lastly, there is, maybe I would like to mention one of these. There is one other class of interesting longevity therapies that, instead of trying to be systemic, as interventions targeting blood or the epigenome are, these ones are more targeted to one specific kind of damage in a specific system. And the one example here is this thing called cyclodextrins. So the idea here is that if the cause of cardiovascular disease is the buildup of cholesterol in the arterial epithelium instead of arteries, right now the only way of avoiding that is, one, you can reduce the rate of accumulation of cholesterol using something called statins or PCSK9 inhibitors. But once the cholesterol is there, how do you get rid of it? Now there's in some extreme cases with big arteries or veins, you can actually do surgery and cut open the veins and actually scrape out the cholesterol. But that doesn't work in general for all arteries, and it's a very messy procedure. And so cyclodextrins there's this company called Underdog Pharma that was spun out of Sense, and they're working precisely on a class of molecules that can actually go, you can inject them and they can go in a very targeted way, go to their arteries and then extract the cholesterol back into our blood so we can actually get rid of it. And this is more powerful than merely slowing down the rate of accumulation of LDL cholesterol, because ultimately you can slow it down as much as you want, but it will still keep building up and it will eventually lead up to damage. So you actually want to bring it back or remove the damage rather than slowing down its accumulation. If you want robust rejuvenation therapy, of course, the ideal case is to combine both a healthy diet with this intervention, so you can actually get both. You can both slow down accumulation as well as removing damage.
So one of the other things first of all, that was a really helpful overview. One of the things that you've written about, and you also spoke about it in a video that you did, which I would encourage people to watch, complimentary to the blog post, the longevity FAQ, was you said you were really excited about the possibility of combining these therapies and doing tests that, where people are not just trying one of these therapies, but multiple, and testing which ones might work very well together. Why is that so important from your perspective? And is there like a sensible place where you might suggest sort of beginning, like certain things that could be work extremely well in combination, or you just kind of broadly want to see things tested together?
Yeah, so first, maybe one brief explainer, because at least to me, it seems obvious that, and from some limited evidence out there, it seems obvious that combining therapies may be very powerful. And the reason why this is not done more often, well, there's one field where this happens, which is oncology. In oncology, the usual drugs that are given to treat cancer are, as a matter of fact, combinations. But the reason here is that because with cancer, the so the FDA is more lenient there, as in they will let you try more things in cancer, because basically if you fail, you just die effectively. Like cancer is a very nasty disease. In other cases, for most other diseases, and especially if you just want to do prevention, they will ask you, if you want to try 3 drugs, they will ask you to do one group, one control group, then one group for drug A, another group for drug B, another group for drug C, one group for drugs A and B, one group for drugs B and C, one group for drugs A and C, and then one group for A, B, and C. Now you can imagine how expensive those kinds of trials would be. So that's one reason why this doesn't happen more often. Oh, and by the way, this will just be for one given dose of each of these drugs. The FDA will actually want to see various doses of each drug to see what happens with each. So it will actually, the combinations will blow up in scale. So ideally here you want to go heavy on mice and then characterize interventions there, and then pick or try to find a way to rationally devise combinations before doing anything in the human case. Now, the problem is that ideally academics would be doing this, but then this kind of thing seems either expensive for an academic lab to do, or it may not lead to necessarily lots of mechanistic insight into one specific pathway that the lab may be interested in. So academics don't seem to be particularly interested in this kind of intervention stuff. It's kind of like a middle ground valley of death situation where you want large scale, like Series A or startup scale funding, but in an academic context, and that's kind of hard to find. I've been kind of trying to work on. I've been working on some of these projects with some collaborators and trying to see if we can get some of this stuff to happen. And some of the interventions that we have been discussing that could be tried together. One starting point would be, well, rapamycin and caloric restriction, again, they even though they work in a similar way, didn't work in exactly the same way. So again, what happens if you combine them? There is also for the immune system. So I mentioned earlier that about the role of the thymus, but your stem cells in your bones also age, or rather their microenvironment, which is the stuff that surrounds them, also ages, which impairs the function of the cells. Now, if you just rejuvenate the thymus, maybe you don't get a very strong effect because the cells themselves that are going into the thymus are also aged. So you want to rejuvenate the thymus and the stem cells. Likewise, there was a recent trial for osteoarthritis, to treat osteoarthritis by this company called Unity, using a senolytic, which sadly ended up failing. But here you could argue, well, osteoarthritis it's a complex disease that is mechanically it's caused by lack of cartilage in a joint. In this case, let's say in your knee. So maybe if you reduce senescent cells, maybe there are other kinds of inflammation still there. And even then, you may also want to use a cell therapy to kind of try to get the cartilage to regrow. So in that case, you could combine a senolytic with a cell therapy, like injecting some stem cells in the joint as well to try to get back the therapy. Which again, if you only try the stem cells, maybe the fact that there is inflammation from the senescent cells would make it so that the cell therapy wouldn't work on its own, but combined, maybe you actually get the effect. Now, I agree with Aubrey de Grey. He says that if an intervention doesn't work well on its own, it probably doesn't work well combined. I think that's true, but I also think that if an intervention works kind of in a weak way, another one works in a weak way, both together, they will probably work not merely in an additive way, but probably more in a synergistic or multiplicative way.
So I guess the last place I'd like to kind of go into is what are some of the companies that are working on some of these therapies that are interesting from your perspective to follow, whether they're sort of running the trials already, like Unity, or maybe earlier stage that are taking sort of novel approaches. I'm just curious to see from like a company and startup perspective what you find interesting right now.
Yeah, so on the reprogramming side, I mentioned, so reprogramming, I think it's kind of early stage, and I don't know if these startups are going to be successful. Actually, some researchers I've talked to privately, that they don't think that it's the right time yet for these startups. But then we had a caveat. There's one that's called Turn.bio, and as well as Iduna Therapeutics. So when I mentioned reprogramming, there are 3 or 4 labs working on this, so it's a kind of like a small world. One of those labs is that of David Sinclair, and he's the one behind this one that's called Iduna Therapeutics. They're trying to, again, do reprogramming to kind of treat aging systemically. Turn.bio, I don't know which team was behind Turn, but they're also trying to do reprogramming. there is, I think this was a Vittorio Sebastiano, I think this lab, I didn't remember the name. Okay, there's also Underdog Pharma. This is just a Sense, I mentioned earlier, a Sense spin-off working on cyclodextrins. There is also Revel, that Revel for I think Falmor Bio, which is working also a Sense spin-off, and they're working on glucosapine breakers. So I guess maybe something I didn't mention earlier. Glucosapine it's this kind of aggregate, so-called crosslink of that forms in between our cells that make our bodies in general more stiff. This stiffness then has downstream effects on the immune system and on the circulatory system and elsewhere. And some of it's quite difficult to kind of break and actually to get this to restore tissues to their or to reverse stiffness. And they're working on that very hard problem. I think they're the only ones working on that extremely hard problem. Other ones, there are also some startups working on longevity in new models. So, for example, there is Celebrity, this company. They're working on aging, or well, I think they actually named themselves to Loyal now. They're working on reversing aging in dogs. And the interesting thing here is that it's seemingly easier to prove a drug for dogs than for humans, and dogs are closer to us than mice are. So perhaps by understanding aging in dogs, we can get some insights for humans. And with dogs, you can also potentially get instead of having to just host the mice, you can have dog owners. They actually are doing the hosting for you, so you may get cheaper trials. So basically, you get people, hey, you want to try this drug on your dog? It's like, well, you pay them some money, but then the dog just goes off, and you just you don't need to worry about that as much as you would have to if you were hosting the mice yourself. Other companies here, I think there's one or two I wanted to mention as well. There is Alcahest that is also, they are working on, they were recently acquired by this Spanish company called Grifols. They're working on plasma or blood-based factors for aging. And I think they were trying to target Alzheimer's. So I guess maybe because right now, well, the FDA doesn't think that aging is IC. So if you're an aging company, you have to pick one target and then go after that. And then maybe go step by step. There is another company that I like that is called Centaura. It's a fairly new company with a very kind of crazy approach, which is that, well, we know that some genes are related to longevity in humans with like these huge gene-wide association studies. And the thinking here is that what if we could engineer a whole chromosome that then goes into a cell? It's what's called as a human artificial chromosome, a whole chromosome that gets somehow, that's kind of tricky to explain how it would do so. But if you can get that chromosome into human cells, then you can get to express a lot of genes that you were not born with. And maybe through that, we can both cure rare diseases as well as get some of those genes that promote longevity into our cells. Because right now, like with gene therapy, you can only deliver a small amount of genes at a time. And with this, we may be able to deliver many at once. I think that if anyone is interested in longevity, I think looking at the gene therapy space is definitely very promising. And then lastly, one final company I want to mention is Gordian Bio, which is also a company funded by the Longevity Fund run by Laura Deming. So Gordian is working on gene therapy as well, on trying to build a platform to be able to like multiplex or simultaneous testing on various therapies at once.
Great. That's super helpful, and I hope some people listening, maybe there's some investors who can go and get in touch with some of these companies, and if they ever need any more money, which all this stuff is quite expensive, they can go and help support them in that way. I think bringing more funding and just attention generally to the space is a large part of why I've been excited to be able to have some people like you on the show so far. Last question, and then we'll wrap up and show and tell people where to go and learn more about your writing and things like that. But last question for you is are there any personal strategies that you've taken? I know there's like not a whole lot to do at this point, but along the lines of like caloric restriction, maybe that you're doing to, hopefully give yourself the best chance you can to live a longer and healthier life. And then secondarily to that, is there anything that you could sort of anticipate being able to or being interesting for you to do yourself in the future?
Yeah, so I personally do intermittent fasting. I try to, I guess this, so proper caloric restriction can be psychologically painful in that you have to be basically hungry all the time. There is this so-called caloric restriction society that there's a group of people that actually do proper CR. Intermittent fasting, you're basically, in my case, I skip dinner. I typically don't have dinner. I just have lunch maybe at 12 or 1 p.m. And that's it until the next day. So from time to time, I do like maybe 1 or 2 day fasts to do like longer periods. And I was thinking of doing like longer, like 1 week fasts for the same purpose. I think that you may get some of the same benefits from CR through something like this. Without the psychological toll of just being hungry literally all the time. I mentioned earlier that CR and things around CR are the most validated ones. So this is why I chose this one. It's also basically free to implement. I also try to follow or it's like my diet. I will eat potentially anything depending on the situation, but usually my regular diet is relatively vegan. I drink this thing called Huel. It's kind of like Soylent, but somewhat better and tastier, and happens to be vegan in origin. There's maybe some debate to be had here about the carnivore diets, keto diets, and other diets. I think that there are various things that can be reasonable, but something I think broadly like a whole foods, plant-based diet or a Mediterranean diet that probably ideal. Other than that, like taking supplements, I don't take any supplements. I think that especially when you're fairly young, and I'm relatively young, I'm 28. I think that I'm not really aged, that there is not much to kind of reverse or restore. So there is not much I think that will be benefit me personally. Rapamycin might, but with rapamycin, one has to be very, very careful. One needs a prescription and one needs close follow-up by an MD so that they can verify that you are not overdoing. Because if you overdo rapamycin, this is something we didn't mention earlier, rapamycin is typically used as an immunosuppressant for organ transplantation. So if you go too far with rapamycin, you end up fucking up your immune system, and you don't want to do that. So you want to be very careful with something like that. There is a company that thinks we're going to start prescribing rapamycin in any state in the US online. I think they're doing this trial now to see if they can actually do that. And I may consider taking it, but I wouldn't do it right now. If I were older, maybe I would be trying to be doing even more CR. I would try to, it's probably the one thing. Again, David Sinclair, for example, maybe I can give examples of other people. David Sinclair himself takes NMN, which is an NAD booster. He takes resveratrol as well with yogurt. I mentioned earlier that his lab has done some of the groundbreaking work on this kind of stuff. But I think other labs and the weight of the evidence, I don't think necessarily this is the right way to go, but there he is if anyone wants to go down the Sinclair route. Laura Deming, last time I talked to her and also online, she will eat from the time like cookies and chocolate and desserts. So it's not like she's following like a strict diet here. And I think online she mentioned that she doesn't really take any supplements either. So I guess like we are all probably expecting or waiting for these more repair-oriented therapies to arrive in the future, so we don't have to kind of suffer in the meantime. Yeah, I think that's probably that. I think the other people in the aging space, I think that probably if you're talking about people in the field, I think that there are all these supplements around and stuff, but I think people are not really overdoing them much. I think once you're kind of broadly healthy and doing exercise and having a good diet and getting good sleep and doing some CR and some intermittent fasting, on top of that, like what are the extra gains from everything else? And does that compensate the cost of doing everything else? That's, to me, it's right now unclear. If you have the basics right, you have most of it already right.
Great. Yeah, that's helpful to know, and interesting the people, beyond just yourself and what they're doing. So, can't thank you enough, Jose, for coming on today. It was really interesting talking about these things, and I find that all of my conversations with people in the longevity space tend to go far past the time that I've scheduled, just because it's like obviously a very deep subject, but just endlessly interesting in terms of like obviously the objective would be to live longer, healthier lives. It's like what more could we ask for than that? So appreciate you coming on and sharing some of your knowledge. We'll point people to where they can go learn some more things in the show notes, but it would be great if you could just kind of tell people where you'd point them to as well.
Okay, great. Yeah, so you can find me at nintil.com, or my Twitter is artirkel, that's ARTIRKL. Kel. And if not, just like search my full name, and there's only one of me, and you can find me there on the internet.